Okay, good morning, everybody. So we are back to flavor physics. Yesterday was a bit of a warm-up. I guess many of the things that we discussed yesterday were familiar to many of you. We will continue today with more about flavor basics, but today we will focus more on flavor symmetries and the breaking of flavor symmetries, what the implications of this breaking of flavor symmetries is, both in the standard model and also beyond the standard model. And I want to start with a very brief discussion about parameter counting, the counting of actual physical parameters. The flavor parameters that we had introduced yesterday were the three Yukawa couplings for the up quarks, the down quarks, and the charged leptons. These are generically complex 3×3 matrices, but not all of the entries of these Yukawa matrices are actually physical. And one can go through this standard exercise that we had briefly reviewed last time, where you go into the mass eigenstate basis, you do these bi-unitary transformations, you use all the freedom that you have to redefine the quark fields, the lepton fields, and you find that you end up with only a small number of actual physical parameters, which are the masses of the quarks and leptons, and then there are 3 mixing angles in the CKM matrix and 1 physical phase in the CKM matrix. So you can get rid of many of those free parameters going through that procedure in sort of a pedestrian way. Some of you might also be familiar with that you can reach this conclusion just looking at the flavor symmetries and the breaking of those flavor symmetries, and this is something I want to discuss now quickly in the following. So the flavor parameters that we have in the standard model are the 3 complex Yukawas. But then the actual physical parameters are only the fermion masses and the 4 parameters of the CKM matrix. And in order to get to this parameter counting of how many parameters you actually have, one can use a rather simple rule. And the rule says that the number of physical parameters is the number of total parameters that one starts out with. Minus the number of symmetry generators that are broken by the parameters that one has introduced. So in general, the symmetry generators will correspond to transformations that one can perform, in this case on the quark and lepton fields, in order to try to absorb parameters. But the symmetry generators that are unbroken, well, they correspond still to symmetries of the Lagrangian. So when you perform those transformations, nothing will change. Those you cannot use to absorb any parameters. So only the symmetry generators that are broken can be used to get rid of parameters. And we can convince ourselves that this works. We can look at a simple example. For example, the lepton sector in the standard model. So there we start out with 1 Yukawa coupling. That would correspond to 9 magnitudes and 9 phases that are our free parameters. So we have 18 parameters in total. 9 magnitudes and 9 faces. And then we can look at the, oh, yes, question.
I think I'm missing something obvious, but how did you get 9?
A 3 times 3 matrix.
Oh, 3, okay.
And then it's a complex, so we have.
Complex, really.
Yes.
Gotcha.
And yeah, so now the next thing then is we have to look at the symmetry breaking pattern. In the lepton sector, we start out with 2 U3 symmetries, one for the left-handed leptons, one for the right-handed leptons. And once we introduce the U-cover for the leptons, we break this symmetry, this flavor symmetry. So we have to think about what subgroup of that symmetry is left. We know that all the leptons have different masses. So once we have introduced the U-cover for the leptons, we're not allowed anymore to have any non-trivial flavor rotations between the different generations. So there won't be any SU3 or SU2 subgroup left over. We also know that if we only have the U-cover for the leptons, we don't have any flavor changing phenomena in the lepton sector. So electron flavor stays electron flavor, muon flavor stays muon flavor, tau flavor stays tau flavor. So what we are left over are individual U1s for the 3 generations of leptons. So we break this U3 squared symmetry to a U1 cubed symmetry, a U1 for electrons, a U1 for muons, and a U1 for taus. And we can also now count how many mixing angles and phases we have in those cases. So here we have the 2 U3s that correspond to 2 times 3 mixing angles and 2 times 6 phases. So in total, there are 6 mixing angles and 12 phases one starts out with. And one is left with 3 phases, the 3 U1s that remain. And now we can combine that to figure out how many actual physical parameters we have. So we start out with 18. And then we get rid of 18 minus 3, which is 3, which can be identified with the 3 masses of the leptons, the electron mass, muon mass, and the tau mass. And if you divide it up into phases and angles or magnitudes, you also see that there's no phase left over in the lepton sector when you do that. And you can do the same thing in the quark sector, that you start out with 3 U3 symmetries for the left-handed quark doublets, the right-handed up quarks, the right-handed down quarks. You have 2 U-cover matrices, 2 complex 3 times 3 matrices. You can go to the same exercise. You have to think a bit what is the leftover symmetry that you have once you introduce the U-cover couplings. And then doing this counting, you will arrive at the usual result that you get 6 quark masses, 3 CKM angles, and 1 CKM phase that is left as physical parameters in the quark sector. Any questions about that? Okay. Then I want to spend a bit more time with those flavor symmetries and the U-cover matrices. So this next topic will be treating the Yukawa couplings as spurions that will allow us to track flavor breaking in flavor changing transitions. We will look at these Yukawa couplings now as objects that break flavor symmetries and how we can understand how flavor changing neutral currents, for example, arise as a result of those Yukawa couplings. So they break the flavor symmetry. And we can formally restore the flavor symmetry if we assign appropriate transformation properties to the Yukawa couplings. And so if we look at the, and if we doing that, one says one treats the Yukawa couplings as spurions, or one promotes them to spurions. And how does that work? If you look at the Yukawa couplings in the standard model Lagrangian, again, we had this yesterday. I will now suppress flavor indices. So we have a coupling of our left-handed quark doublets to the right-handed up quarks with the up Yukawa, and analogous expressions for the down quarks and also for the leptons. Yes. Oh, sure. And so if you look now at the flavor symmetry transformation properties of the various terms, for example, the first thing here, if we only focus on the non-trivial flavor transformation, so the SU3 part of the flavor group, then this Q field here, or the Q bar, that would correspond to an anti-triplet of the SU3 that acts on those left-handed quark fields. And the U, that would be a triplet of SU3U. And accordingly, the D would be a triplet of SU3D, and the L and the E would be triplets of SU3L and SU3E. So in order to formally restore the symmetry, this Yukawa coupling by U, that should counteract these transformation properties. So this YU should correspond to a triplet under the SU3Q symmetry and an anti-triplet of the SU3U symmetry. And in that way, this first term would be formally invariant under the flavor symmetry. And the same thing we can do for the other Yukawa couplings, the down Yukawa, that should transform as a triplet under the SU3Q symmetry, and the 3 bar under the SU3D, and the lepton Yukawa, that should be a triplet under the SU3L and the anti-triplet under the SU3E. Yes?
What's the purpose of restoring the flavor symmetry?
Yeah, so this will allow us to track where those Yukawa couplings have to show up in, let's say, flavor-changing amplitudes of certain processes. It's something that you're probably familiar with when you do just a dimensional analysis, for example. There, instead of using a flavor symmetry to track certain properties, you use essentially scale invariance. You look at the transformation property of object under scaling, of changing the energy scale. So by doing dimensional analysis, you just keep track of the mass dimension of certain quantities you have and combine them in a way that corresponds to the mass dimension of the object that you're actually calculating. And similar here, we will be tracking the flavor transformation properties of the various flavor breaking terms that we have, these Yukawa couplings, and how they then show up in flavor changing amplitudes. That's exactly what we will be doing next. We will now make use of these transformation properties to check how these Yukawa couplings show up, let's say in an amplitude for a rare B decay. And let's look at the example that we also yesterday, the decay of a B sub S meson into mu plus mu minus. And if you look at the quark side of that process, that's a transition from a B quark to a strange quark, or an anti-B quark to an anti-strange quark. And last time we've drawn an example diagram how that process arises in the standard model. It goes through the weak interactions, interactions of the W boson with the B quark, strange quark, and up-type quarks. Because it's a weak interaction, there will be left-handed quarks involved. So what we can look at is then overall a current that involves a left-handed B quark and a left-handed strange quark. So for example, we will have such a current that describes this transition from a B quark to a strange quark. And now we can ask, how do these Yukawa couplings need to combine in order to give rise to such a flavor transition? So what we have here, left-handed B quark or left-handed strange quark. So those are parts of the of this Q field, of this triplet under the SU3Q symmetry. So we have here a SU3 part of a SU3Q triplet, and here part of SU3Q anti-triplet. So what we can in principle, we need that we have formally restored the flavor symmetry. Also, this amplitude should be invariant under that flavor symmetry. So we have to construct some invariant where we have, on the one hand, a SU3Q triplet and a SU3Q anti-triplet. So we could just combine those two triplets into a singlet, but that would correspond to no flavor change at all. Yes?
Is the diagram that you showed yesterday where this interaction happens through like the weak interaction,
yes,
is that dominant enough that we don't have to consider any other processes?
So that diagram that I showed was an example diagram of sort of dominant class of contributions that we have. And now using this spurion analysis, we will sort of recover the generic results that we got last time. The same CKM structure that we saw last time will show up when we do this.
Okay.
Now, what we could also look at other currents that could contribute to such a decay process. Look at currents that involve, for example, right-handed quarks, or right-handed on one hand, left-handed on the other, things like that. And we could go to the same exercise that we do now and figure out what the properties of those amplitudes would be. And we would find that those additional amplitudes that can in principle be there have to be strongly suppressed by some small Yukawa couplings. And that the same result we could reach also by just doing a more extensive calculation of these loop diagrams, taking into account not only the ones that I've showed, but also additional ones, which will turn out to be all very small.
So we're not only thinking about that one diagram, but we are thinking about that class of diagrams.
Yes, so we are. When we talk about this process, now we should think of all the diagrams that contribute at the same level, which have external left-handed quarks in this case. But we won't actually look at the diagram. We will just use these symmetry arguments now to determine the structure of the amplitude. Okay, so again, so we have a triplet here, an anti-triplet here. We could combine them into a singlet, but if we do that directly in that way, so if we basically insert no Yukawa coupling whatsoever, then we would just get flavor conserving transitions from a B to a B, a strange to a strange, from a down to a down. So we need to have some Yukawa couplings that give rise to flavor change. So what we need is not a singlet, but an octet that we insert, a SU3Q octet that we insert between those two quark fields in order to get some non-trivial flavor change. So how do we get an octet of the SU3Q symmetry? Starting out with those Yukawa couplings that you have available. There are many options. Sort of the simplest ones are the following. We could have a YD dagger. So we take two down Yukawas and multiply them together. If we do it in that order, first a YD and then a YD dagger, we get rid of the transformation under the SU3D, and we're only left with the SU3Q transformation, and combined in that way that indeed corresponds to an octet of SU3Q. So if we insert now this combination of Yukawa couplings into that current, or if we combine that with those external quark fields, the problem is that we have now down quark fields, and combine that with down quark Yukawas. So if we go into the mass eigenstate basis, these down Yukawas will be diagonal. So we're just left with a diagonal down quark Yukawa coupling squared, which again doesn't lead to any flavor change. We would only get a transition from a B quark to a B quark, strange quark to strange quark, down quark to down quark. So if we go to the mass eigenstate basis, we get a down Yukawa, the diagonal version of the squared, and we want to get a transition from a strange, from a B to a strange. So we have the 2-3 entry of that, but that is again 0. So we don't have any flavor change from this combination of Yukawa couplings. The other option that we have is to insert up-type Yukawa couplings. Again, if we take YU times YU dagger, the SU3U transformation drops out, and we're only left with an octet of SU3Q. And again, we go now into the mass eigenstate basis. And we have external down-type quarks, but up-type Yukawas. So now we don't get just the diagonal up Yukawas, but we have CKM matrices that show up on the left and right side of those Yukawa matrices, because our unitary transformations that transform the down quarks into mass eigenstates are not the same that transform up quarks into the mass eigenstates. There's a CKM matrix that this misalignment, or that parameterizes this misalignment between the up sector and the down sector. So if we take this thing and go into the mass eigenstates, we get the following. We get a CKM matrix daggered and a diagonal up Yukawa squared and another CKM matrix, and we want the 2-3 entry of that combination. We have this up Yukawa, the diagonal up Yukawa squared, the 1-1 and the 2-2 entry correspond to the Yukawas of the up quark and the charm. Those are very small. So to a good approximation in that case, we can neglect them and only keep the entry, the 3-3 entry corresponding to the top Yukawa. So to a good approximation, that then corresponds to VTS star times VTB times the top Yukawa squared. And this combination of CKM matrix elements, that's exactly the same thing that we saw yesterday when we did this example diagram, and we looked at these loops which had top quarks, charm quarks, and up quarks in it. We had to sum up all of them. We had to use unitarity of the CKM matrix, get rid of some of those expressions. Again, we neglected the up quark mass and the charm quark mass, similarly as we're neglecting here the corresponding Yukawa couplings, and we get the same combination of CKM matrix elements in this amplitude. Yes?
Are we looking for octets because there are 8 generators of SU3?
What we want is something that we want an amplitude that is invariant under the flavor symmetry. And we have this quark current which has a SU3Q triplets and an triplet and an anti-triplet. So we have to have something which combined with a triplet and an anti-triplet gives a singlet. And the options you have is either a singlet or an octet. These are the options that you have to construct a singlet out of those objects. What we had last time looked a bit different in terms of this Yukawa coupling of the tops that shows up here. So what we had last time was a loop function that was still depending on the top mass. So it's not just the Yukawa coupling squared, but some generic loop function of the top mass, or you can think of it, a loop function that depends on the top Yukawa coupling. But if you remember also from last time, this function had a specific structure. So from yesterday, we saw that the corresponding amplitude had the same CKM structure, and then we had a loop function f that depended on xt minus f0. And so if you think of this f of xt in terms of a Taylor expansion, you would, if you start at 0, and then you would get the first term, which is proportional to xt, and you subtract the sort of the zeroth order term, the f0. So you start out with a term that is linear in xt, and then you will get higher and higher order terms. So this f of xt minus f0, this minus f0, that exactly gets rid of a possible constant term that would be inside here, and we recover sort of this proportionality to the top Yukawa that we had on the other side. And well, in general, there's this loop function. So in general, we would not only have this YU dagger that would lead to a flavor change, but we would have higher and higher powers of up Yukawas that we could also insert that combine into an octet, and that could give rise to this flavor changing amplitudes. So that term that we get here is sort of the first term in a Taylor expansion of the actual amplitude.
Can you determine only the power of this Yukawa?
So what you can determine is sort of the leading term that should arise, the leading CKM structure that should arise in that way. In principle, is that you can have higher and higher powers of this YU dagger. You can write a YU dagger times YU dagger. If you go to the mass eigenstate basis, that would give here a YU diagonal to the 4. That should also arise in principle. It has the same structure in terms of CKM matrix elements, but a Y top to the 4. That can also arise, but it doesn't give anything, any new flavor structure in that sense. If you look at other transitions, for example, transitions which involve right-handed down-type quirks, then it's a very useful exercise to convince yourself that those are indeed suppressed. So in order to get flavor change in the standard model of currents that involve right-handed down quirks, you necessarily need at least 4 Yukawas that show up, and 2 of them have to be down-type Yukawas. So, for example, this current, if you would have a right-handed B quirk going to a right-handed strange quirk, that current would be necessarily suppressed in the standard model by a bottom Yukawa and a strange Yukawa times a structure that looks like that. So it will be much, much smaller than this left-handed current that we have here. Other questions about that? Yes?
How can we Taylor expand if EXT is greater than 1? Because EXT is just is greater.
Yes. You would have sort of if you write out what this function actually is, you would have a sort of a prefactor of that comes with xt. So if you send xt to 0, this function goes to 0 in that sense. Okay. Yeah, as I said, one can go through this exercise with all possible flavor changing transitions that you can come up with. You can do it with flavor changing little current transitions. You can do it with charge current transitions, left-handed quirks, right-handed quirks, and in each case you will figure out what is the leading CKM factor that you get in those cases, and whether or not you will be suppressed by additional small parameters that make certain contributions negligibly small. So these Yukawa couplings, you can think about them as sort of the basic building blocks in the standard model that lead to these flavor changing transitions, and it can be useful, or at least I find it useful to think a bit more about those Yukawa couplings and how they sort of define directions in a flavor space. So these objects that we looked at, this YU dagger or YD dagger, these combinations of Yukawa couplings, they define directions in these SU3 flavor spaces. We could also multiply them in the opposite way, a YU dagger YU or a YD dagger YD. So they define directions in flavor space, and sort of symbolically we can try to illustrate that So let's say this is a SU3U flavor space. This YU dagger YU that lives in SU3U flavor space. The SU3Q transformation properties of this combination drops out. So this is a singlet under SU3Q, but it's an octet under SU3U. And we can think of this thing pointing in some direction in this flavor space. Similarly, if you look at the SU3D, there will be the Y down dagger, Y down that points in a particular direction. And then if you look at SU3Q space, now we have here two combinations, YU dagger and YD dagger. And that would be one way to sort of get a simple intuitive understanding of why there's this mismatch between the number of parameters that are inside these Yukawa couplings and the actual physical parameters. Yeah?
So what are the angles in this flavor space representing?
Yeah, so those correspond in some sense to the I don't know how to say it other than I said before. So some direction in flavor space that is sort of determined by those combinations of Yukawa couplings. If you think of, you can decompose that, you could decompose those Yukawa combinations in terms of SU3 generators, and that would tell you then what's the linear combination of generators that corresponds to those Yukawa couplings. Yes? Oh, that's just symbolically that's meant to be in this SU3 space. So I guess we could draw an 8-dimensional thing where each axis corresponds to a generator of SU3. But I guess the intuitive picture that I want to convey here is that the actual absolute direction in flavor space that those Yukawa couplings point to, that's not a physical thing. It's only when you have two of those objects living in the same space, then the relative orientation of those two things is actually a physical thing. And what's also physical would be the lengths, if you want, of those vectors, which would correspond to the eigenvalues of those Yukawa couplings, that would correspond to the mass eigenvalues of the quarks and leptons. Yeah.
So literally, these are just vector space of 8 constants.
Yes. Yes. So the actual physical parameters are the eigenvalues, or the lengths of those things, and the relative direction here in SU3, Q flavor space of the YU dagger and the YD dagger. So this angle, in some sense, that corresponds to the CKM matrix. Yeah.
Maybe you explain this a little bit. Why is this Y dagger a secret under all these groups? Why does it have non-trivial? Why isn't the dagger the opposite of whatever the non-dagger?
Oh, yeah. So what I guess to get a total singlet, you would then now take the trace of that thing. That would get rid of all the flavor transformation properties, right? So you start out with a matrix, you multiply it with another matrix. That's still a matrix which has sort of these two open indices which correspond to a non-trivial transformation of the flavor groups that these indices correspond to. So to get a total singlet, you would need to take the trace of that thing. More questions about that? Okay, so we will come back to this sort of symbolical picture when we now go beyond this, the standard model and introduce new sources of flavor violation, additional sources of flavor violation. And then in many cases, whenever you add new sources of flavor violation, you can again think of them living in some of those spaces. And then most of the time, when you introduce new parameters, new flavor parameters, they actually will correspond to something physical because you already have some directions defined by the standard model you cover. So once you add new things, the relative orientation of the standard model you covers and those new sources of flavor violation, they will correspond to actual physical sources of flavor violation that can modify flavor changing processes. So let's see how that works. There are various approaches of how to go beyond the standard model. I guess generically you can either think of the standard model as an EFT and add higher dimensional operators in the framework of the standard model. EFT is MEFT, and you probably have heard about that earlier, and I think the first week in the lectures by Anish. I assume you have heard a lot about that. Or you can add explicitly new degrees of freedom, some light degrees of freedom, axions, dark photons, stereo neutrinos, other light particles to the standard model explicitly, and study how those new particles couple to standard model degrees of freedom. So very generically, our Lagrangian would be the standard model Lagrangian plus other things. In terms of an EFT, we would have an expansion in 1 over some new physics scale lambda. So we will have a tower of operators with their Wilson coefficients, dimension 5 terms, dimension 6 terms, and so on. Or explicitly light degrees of freedom. That are coupled to standard model fields. And again, you can couple them in terms of such an EFT expansion. You start out with the lowest dimensional operators, a handful of so-called portal operators that can connect these light degrees of freedom to the standard model. But you could go to higher orders and again do such an expansion at dimension 5 terms, dimension 6 terms, et cetera, et cetera. Yes? Yes?
Symmetries are global and not good. Why is the absolute direction not physical?
I mean, why would it be physical? I mean, those directions, I mean, you can sort of arbitrarily choose what you call an up quark, a charm quark, and a top quark, for example, without having Yukawa couplings. So it's only these Yukawa couplings that define what an up quark, a charm quark, and a top quark actually is, and that defines sort of a choice of bases in that space. So the sort of the first object that you insert there that defines your basis you would start with. Once you add additional things into those spaces, then the direction of those objects relative to the Yukawa coupling, so it would be the actual physical things. Does that make sense? Okay. So coming back to this picture, well, now on the one hand, these Wilson coefficients of these higher dimensional operators, if those higher dimensional operators contain fermion fields, quarks and leptons of different flavors, those Wilson coefficients, they will correspond to new sources of flavor violation in addition to the standard model Yukawa couplings. And similarly, these couplings of these new degrees of freedom if they couple to standard model fermions, they can constitute new sources of flavor violation. And in many cases, new sources of flavor violation are very strongly constrained by existing measurements of flavor changing processes. And the canonical example are dimension 6 operators in SMEF that would contribute to meson oscillations. Yeah.
The same measurements constrain a fourth generation, and if so, how strongly?
Yes, in principle, yes. Now, if you introduce a fourth generation, a chiral fourth generation, that's now excluded by many other things as well. But yes, those also would receive very strong constraints from flavor transitions. A fourth generation in this language that I'm using here is a bit more tricky to describe because now the Yukawa couplings would be not 3 times 3 matrices, but 4 times 4 matrices. So now the question becomes how you actually want to formulate this story. You want to take sort of these 3 times 3 sub-matrices as the actual standard model sources of flavor violation. The problem is that now your rotations are not necessarily unitary anymore, so this becomes a sort of a more complicated discussion in the language that I'm using here. But yes, fourth generations, if they mix significantly with the 3 usual generations, they would be strongly constrained by flavor changing processes. Okay, so the example I want to discuss is meson mixing. And we can look at four fermion contact interactions that can contribute to meson mixing. In principle, there are 4 different neutral meson systems that we can consider. There are neutral kaons, neutral D mesons, neutral B mesons, and there are both the B0 and the B sub S mesons. So we have 4 systems in total where we have this phenomenon of meson oscillations. And in each of those 4 cases, at low energies, one can write 8 four-fermion contact interactions, 8 independent four-fermion contact interactions, which all potentially contribute to meson mixing. So at low energies, there are 8 dimension 6 operators. That contribute, and let me write them down for kaon mixing. And there are different notations and different conventions how to define those operators. One set of operators is the following. We can have a left-handed strange quark connected to a left-handed down quark, and that thing squared. So 2 currents that give a transition from a down quark to a strange quark. Then there's a corresponding V right-right operator where instead of left-handed fields, there are right-handed fields. Then there's an operator that is sometimes called Q1, left-right, that would have 1 current with left-handed quarks, 1 with right-handed quarks. Then there's a Q2, left-right, which again has right-handed and left-handed quarks mixed, but now with scalar currents. So S right, D left, multiplied with a S left, D right. And then there are a few more. There's a, can you still see when I write down there? No. Okay, so I should move over here. A Q1 S left left. That corresponds to a S right D left squared. And then there's the corresponding S right right version of that where you exchange left and right. And then there's also a Q2 S left left, and that has a tensor structure, sigma mu nu between the quark fields S right, sigma mu nu D left, and that's squared. And again also a Q2 S right right with left and right exchanged. So these are a set of independent dimension 6 operators that contribute to kaon mixing. And that respect SU3 color and U1 electromagnetism. Yes.
At these low energies, are we still in the realm of perturbativity for strong interactions?
No. So if you really want to compute what the actual amplitudes for kaon mixing is based on those operators, what you need to know are then hadronic matrix elements, where you take one of those operators, you put a kaon on one side, an anti-kaon on the other side, and you need to compute what that matrix element is. And well, kaons are very light, and at that scale, QCD is non-perturbative, so you need non-perturbative methods to actually calculate the actual hadronic matrix element of that process. So things like a lattice QCD would give you these matrix elements. There are sort of quick and dirty estimates of how big those matrix elements would be. It's known as the vacuum insertion approximation, where you say, well, you have these two quark currents, and you want to go from a kaon to an anti-kaon, let's say. And one way to do that would be you go first from a kaon to the vacuum, and then from the vacuum to the anti-kaon. And that essentially gives you kaon decay constants, a square of kaon decay constants. That would be a sort of a simple way to get an order of magnitude estimate of how big those matrix elements are. But if you really want a precise answer, you would need non-perturbative calculations of those matrix elements. Good. So those 8 operators, they give kaon mixing, and they respect SU3 color times U1 electromagnetism. They don't. Not all of them respect the full electroweak gauge group of the standard model. So if you look carefully through those operators, you will find that there are some of them which actually are not invariant under the SU2 left cross U1 hypercharge gauge group. So those operators, you would expect that they have Wilson coefficients which are actually secretly coming from them, maybe dimension 8 operator or something like that, and that they are suppressed by the Higgs vacuum expectation value divided by some new physics scale squared. Historically, people had looked at those meson mixing constraints with the idea that there might be new physics around the electroweak scale, and in that case, it makes sense to keep this set of operators, which are only invariant under SU3 color and U1 electromagnetism. If there's a significant gap between the electroweak scale and the new physics scale, then yes, that some of those operators would have suppressed Wilson coefficients, as they would correspond to actually dimension 8 operators in the context of SMEFT. And if you think to some new physics scenario, there are many ways of how such operators could be generated at low energies. For example, in the context of supersymmetric models, there could be loops of gluinos and squarks. When you integrate those things out, you would end up with those 4 Fermi contact interactions. You could have scenarios where you have a Z prime gauge boson, which for some reason has flavor-changing couplings and couples to strange quarks and down quarks. Integrating that thing out would give those 4 Fermi contact interactions. You could have, in extra-dimensional models, you can have Kaluza-Klein excitations of gluons, which might have flavor-changing couplings. Integrating those out might give these 4 Fermi contact interactions at low energies. So just pictorially, these types of operators may arise from integrating out some heavy new physics particle So in the simplest case, we could have something like that, something called X that couples in a flavor-changing way to strange quarks and down quarks. And when you integrate that out, you would end up with exactly such a 4 Fermi contact interaction. And which one of those operators you get, that will depend on the coupling structure of that new object. And if we stay with that EFT picture, this picture of effective interactions, then we will get a contribution in that case to kaon oscillations. So the amplitude for now a kaon mixing would be the Wilson coefficient of one of those operators, for example, this VLL operator divided by a new physics scale squared, and that should compare to the corresponding mixing amplitude in the standard model, which generically will come from the weak interactions. It will have a Fermi constant, it will have a loop suppression, and it will have a suppression by CKM factors. In the case of kaon mixing, you have something like that, a VTS VTD squared. So that's sort of a generic new physics contribution. While this is sort of an estimate of how big the corresponding standard model contribution is. And because the standard model contribution is very, very small, it's suppressed by this loop factor and by small CKM matrix elements, you have, in principle, very, very high sensitivity to a new physics effect. If you assume that this Wilson coefficient is order 1, or if you say that in this simple picture here that the coupling of that new thing, these flavor-changing couplings are order 1, then you will get a very, very large contribution that is only suppressed by the mass of that new object or by the new physics scale. And are we already out of time? No, we still have 10 minutes, right? Good. So in general, you get very, very stringent constraints in this EFT picture. You can translate now the existing measurements that we have on meson mixing and combining these measurements with standard model predictions into constraints on how big those new physics contributions could be. So overall, there's a pretty good agreement between standard model predictions for meson mixing and the experimental results. Which allows one to derive constraints on the new physics. And for example, one finds the real part of such a Wilson coefficient that would correspond to an operator contributing to K-on oscillations divided by the new physics scale squared has to be smaller than around 1 over 10 to the 3 TeV squared. Or even more extreme, the imaginary part of another of those Wilson coefficients, the C2 left-right, the Wilson coefficient of the 2 left-right operator, again for K-on oscillations, so the SD entry of that Faber matrix, that should be smaller than around 1 over few times 10 to the 5 TeV squared. If they were any larger, we would have already seen some significant discrepancies in those meson mixing measurements. Yes?
I think you said you were going to talk about this in later lectures, but is this the same type of analysis we'll do for the B anomalies that exist?
Yes, essentially yes. That's the same basic setup, but now we will have, in the case of the B anomalies, there actually is now a discrepancy between a standard model prediction and a measurement, and then you sort of interpret that now as a hint for the existence of such a new contribution. Then one would write down the operators that would contribute to those rare B decays where the anomalies show up, and then you can try to identify what is the corresponding scale of new physics that corresponds to such an effect, and you try to identify if there's any operator that actually could give an explanation of those B anomalies. Yeah, so we will come back to that on Thursday. Yeah. Yes, what is usually done is one takes into account one at a time. There could, in principle, be cancellations between different operators. So you have multiple of them, then you can have, in principle, cancellations. Generically, you wouldn't expect to have dramatic cancellations. It could happen in certain new physics models that not only one of them is dominant, but you have multiple, but usually they don't conspire to and cancel out. But yeah, if you have an actual new physics model that would predict that there are several of those Wilson coefficients and there might be certain relations that you can predict in your model, then you probably should redo this analysis in a way that you have all of them switched on simultaneously. Yes?
Is there a difference between operators that receive standard model contributions and operators that are purely new physics operators in terms of the bounds?
Yes. So I should have mentioned that in the standard model, the operator that you get is this QV left-left, so which has all left-handed fields involved. And actually, the constraint on these other operators, in particular, in the case of K-on mixing, tend to be actually stronger than the constraint on the standard model operator. I guess you can already see it also here. Here's the Wilson coefficient that you have already in the standard model. That constraint is actually quite a bit weaker than the constraint that you get on some of those other operators. The reason in the case of K-on mixing is that these hadronic matrix elements turn out to be enhanced for those other operators. If you look at at kaons, they are pseudoscalars. So to get non-zero matrix elements with only left-handed quarks, you sort of internally you have some chirality flip showing up on those quarks. But if you have now such a left-right operator where you have both left and right-handed fields, then you don't have to do that. So these operators, they give hadronic matrix elements which are enhanced by the kaon mass over the strange mass squared, which is quite a large numerical factor. And that's why you get much stronger constraints for those guys. Now, usually we would like to have new physics not too far above the electroweak scale. And there are many motivations why we would like that. Most of all, the Higgs naturalness problem, which would lead you to expect that there should be new physics not far above the electroweak scale. So how can one reconcile having new physics, let's say, not far above TeV with those very, very stringent flavor bounds? And well, I mean, the one way to avoid the flavor bounds, sort of the simplest way would be just make the new physics scale very heavy, so to just decouple all the new physics. But if you want to keep new physics at rather low scales, then you have to make these Wilson coefficients small. So what are the strategies to avoid flavor constraints? Sort of the simplest thing would be to make the new physics scale large. So you just decouple everything. But that's something you might not want to do. So other options, you could assume that the new couplings have a trivial flavor structure. So basically, they correspond to unit matrices in flavor space, similarly to the gauge interactions in the standard model. And in that case, no matter in which basis you rotate, you wouldn't get any flavor changing effects, at least at tree level. Or if you allow for at least some amount of flavor violation, you can assume that these new flavor-changing couplings, say, in quotation mark, point in the same direction as the Yukawa couplings. And you can do that either approximately or exactly, as exactly as possible. So you can, on the one hand, you could assume that the new couplings are proportional to Yukawas. That's sometimes referred to as the concept of minimal flavor violation. So there you say that the Yukawa couplings are the only spurions that break the flavor symmetry, and all other couplings have to be functions of the Yukawa matrices. And that way you sort of have aligned all these new couplings with Yukawas, and you don't get any new sources of flavor relation. All flavor relation will be proportional to the same combinations of CKM matrix elements that one also has in the standard model. And that means these Wilson coefficients, they will be suppressed by the same CKM structures as in the standard model, and therefore are very small, and one can live with much lower scales of new physics. Or you can also try to do this alignment in an approximate way. So now you not necessarily have these new couplings being proportional to the Yukawas, but they are at least approximately diagonal in the same basis in which the Yukawa couplings are diagonal. One way to approximately align the new couplings would be to assume that the new couplings, they that this new physics talks only to the third generation. Because Yukawa couplings, well, also they mainly involve the third generation. The Yukawa coupling of the third generation are much, much bigger than the Yukawa couplings for the first and second generation. So if the new physics only talks to the third generation, you have this approximate alignment, and then flavor changing processes tend to be also strongly suppressed, and you tend to be safe from flavor constraints even with a rather low scale. We're over time already? Okay, sorry. Sorry about that. Yes, so I guess tomorrow we will just very quickly wrap this up, and I want to make a few comments about sort of the big picture, what the role of flavor is, and then we move on and talk a bit more about how to actually measure the flavor parameters in the standard model and how to explain the hierarchies that we observe in the flavor parameters. Okay, thanks.